Welcome back to Math 151. In the last video, we were considering limits that look like this. We have a base function which is changing, and a power function which is changing. And when we use substitution, we get one of the exponential indeterminate forms, like 0 to the 0, 1 to the infinity, or infinity to the 0. And we develop the following strategy for computing these limits. We set y equal to the limit that we're interested in, and then to compute it, we start by taking the natural log, which allows us to bring that power function down, computing this new limit of the power function times the natural log of the base function, and then finally raising e to that power. Now the real work comes in step 2, when we have to compute ln y, when we have to compute a limit. This is almost like starting a new limit problem in the middle of our bigger exponential limit problem. But it's also easy to forget about step 3. So that's why it's really important that as you're using this method, you write down what you mean. So you write down y equals the limit you really want, and then as you're working, as you're going through the computation, you write ln y when you mean ln y. That will remind you at the end that in order to get back to y, you have to raise e to that power that you calculated. These are the 3 exponential indeterminate forms, the 3 forms where you want to use this method. So far, we've only seen one example of this method. Let's see a few more. Suppose we want to compute this limit. X plus sine pi x, all raised to the 1 over ln x, and then x is going towards 1. Substitution tells us that this limit is of the form 1 to the infinity. So this is one of the exponential indeterminate forms, and we do want to use the method that we've developed here. We always begin by setting y equal to the limit that we want to compute. Then, in step 1, we write ln of y equals the limit of the natural log of this whole thing. And we always use the log rules to bring that power down. In this case, we get the quotient ln of the base divided by ln x, because our power was 1 over ln x. Now we're ready to move on to step 2, which is to try to figure out what this limit is. In this case, when we use substitution, we get ln of 1 on the top and ln of 1 on the bottom, also known as 0 divided by 0. That means we're in position already to use L'Hopital's rule. A lot of times in step 2, you're going to have to do some kind of manipulation, but here, we're already ready to do it. When you use L'Hopital's rule, as I said before, it's a good idea to make note of it. Pause the video for a moment and think about what you would get from applying L'Hopital's rule here. Are you ready? On the bottom, we're just taking the derivative of ln x, so we get 1 over x. But on the top, we have a composition, so we have to use the chain rule. We get 1 over whatever's inside, but we also have to multiply by the derivative of the inside. So we get 1 plus the derivative of sine pi x. That's pi cosine pi x by another application of the chain rule. Now that L'Hopital's rule has been carried out, we're ready to try substitution again, see if we either get something conclusive or we get another indeterminate form and we have to keep working. Pause the video for a moment and think to yourself, what do you get from substitution here? So in this case, what you should get is 1 minus pi. On the bottom, we have 1 over 1, and on the top, we have 1 plus pi times cosine pi, also known as 1 minus pi, and on the bottom, just 1. So altogether, 1 minus pi. So what's the answer to the original question? Well, this 1 minus pi is not equal to y, it's equal to ln y. So we're not done yet, we need step 3. Y equals e to the whatever I got in step 2. E to the 1 minus pi. And that's the end of the example. We've seen some examples of the form 1 to the infinity. Let's look at some others. Consider the following two simple limits. First, we have the limit of x to the 0 as x goes to 0 from the right. So we should think of x as being a small positive number. When you have any kind of positive number and you raise it to the 0th power, you get 1. So we're taking the limit of 1 here, and that gives 1. What about 0 to the x as x goes to 0 from the right? So 0 raised to a small positive number. Well, 0 raised to anything positive is still 0, so this limit equals 0. Both of these limits are of the form 0 to the 0, which shows that 0 to the 0 is indeed indeterminate. Just by observing something has the form 0 to the 0, we don't know what kind of limit it's going to give us. So, what do you think about the following? What happens if we let both the base and the exponent go to 0? If we have x to the x, as x goes to 0 from the right, maybe this gives us 0, maybe it gives us 1, or maybe it gives us a new number entirely. We can't tell. We'll go through this example in more detail in the next video. There's still one exponential indeterminate form left, namely infinity to the 0. Here are three limits of the form infinity to the 0. We'll see momentarily that these three limits all give us different answers. Let's go through them one at a time. First, we have the limit of x to the 1 over x as x goes to infinity. As always, we start by taking the natural log. Log rules let us bring down the 1 over x, and we get ln of the base divided by x. This is of the form infinity over infinity, which is itself an indeterminate form, and one that we can use L'Hopital's rule on. Here, the top and the bottom functions are both easy enough to differentiate that we see right away this new limit gives us 0. So we have ln of y equals 0, and that lets us conclude that y equals e to the 0, which is 1. Next, we have the limit of x to the 1 over ln x, as x goes to infinity. We do the exact same procedure as before, start by taking the natural log, and now we have to figure out what the limit of that thing is. In this case, the numerator and denominator just cancel out, and we get the limit of 1. So ln y is 1, which allows us to conclude that y is e. You might also notice instead that x equals e to the natural log of x, because e to the x and ln x are inverse functions. So x to the 1 over ln x is literally e to the 1, is literally e. If you notice this at the beginning, then clearly we're saying y is the limit of e, which is just e. So that would be sort of a shortcut way to do this limit. But if you didn't notice, our method still works. Finally, we want to consider the limit of x raised to the 1 over ln of x. X is still going to infinity. We're still going to start with taking the natural log. And now, carefully analyzing this quotient, we see it is again of the form infinity over infinity. On the bottom, the inside ln x is going to infinity. And so we're taking the outer natural log of a bigger and bigger thing. That means that's also getting bigger and bigger and going to infinity. So just like in the first example, we can use L'Hopital's rule. It's easy enough to take the derivative on the top. What about on the bottom? Think to yourself for a moment, how would you differentiate ln of x? You should get 1 over ln x times 1 over x. That 1 over x is coming from the chain rule. Now the 1 over x on top and bottom cancel, and this simplifies to give us just the limit of ln x as x goes to infinity. That's infinity. So finally, we can conclude that y is e to the infinity, which is just infinity. So here are those three limits that we just computed, all of the form infinity to the 0. And we didn't just do three similar examples so you can get used to this method, but also for a conceptual insight. Look at what's happening here. When you think about infinity to the 0, the infinity is telling you something is getting bigger and bigger. But the 0 in the exponent makes it seem like it should go to 1, right? Anything to the 0 should be 1. On the other hand, infinity raised to any power should be infinity. So there's actually sort of a tug of war happening between the base function and the power function. In the left function, the base function is not growing fast enough to keep up with how quickly the exponent is going to 0. So the 0 wins, and we get 1. On the right-hand side, the exponent is going to 0 much, much slower. That's because instead of 1 over x, we have 1 over log x. Log x is a very slow-growing function, so 1 over log x is going to 0 very slowly. And so now the growth in the base wins, and this limit becomes infinity. In the middle, these two forces are in balance, and so you get a limit between 1 and infinity. In all three exponential indeterminate forms, you can see this perspective of a balance between two forces, or one of the forces winning over, when you look at a limit. You should also compare this to what we see in exercises 57 and 58 of the textbook. There we can see something similar happening, with different limits of the form 1 to the infinity. Please go on to the next video for further discussion and examples of our three-step method.